This is a walkthrough of the second Pure paper, A-level paper, and it's a specimen paper from Edexcel. Question number 1. Figure 1 shows a circle with centre O, and the points A and B lie on the circumference of the circle. The area of the major sector shown shaded in figure 1 is 135 centimeters squared. So the area of this shaded bit here is 135 centimeters squared. The reflex angle AOB is 4.8 radians. So reflex angle, that's going to be an angle that's bigger than 180. So that's the angle over here. And that angle there in radians is 4.8. Find the exact length in centimeters of the minor arc AB. So that's this length here. Let's highlight that. So we want to find the length of this bit here, that minor arc. And we need to give our answers in the form A pi plus B. So A pi plus B, where A and B are integers to be found. So A and B are going to be whole numbers. Right, well, the first thing that we need to do is we need to find the length of the radius, and we can use this area that's known over here to do that. So let's start by finding the area. Now, what we know about the area of a sector is it's half r squared theta, where theta is in radians. So I know the area, that's 135. So just write that down, 135, and then half r squared times by that angle subtended at the centre in radians, which is 4.8. So let's rearrange this to make r the subject. So we can times both sides by 2, so we'll get 270 is equal to 4.8 r squared. Then we'll divide both sides by 4.8, so we've got 270 divided by 4.8 is r squared. So r is going to be the square root of 270 over 4.8. That gives an exact answer of 15 over 2, or 7.5. Okay, so there's my radius. Let's just pop that on the diagram. So 15 over 2 centimeters is my radius. Now I know the radius of the circle, and I can work out the angle subtended at the center. That is 2 pi minus 4.8. I can use that to work out the length of the arc, and then the length of arc formula is equal to r theta. And since it's the minor arc, it's going to be r, which is 15 over 2, times by that angle at the center. Now we want to find the angle which is on this side over here, the minor angle AOB, or the angle which is less than 180. Now we know all the way round in radians it's 2 pi. So 2 pi minus 4.8 is going to give me this angle on the other side. It's a bit like doing 360 minus the angle that you know to find the other one. So what we're going to have here is 2 pi minus 4.8. Let's multiply that out and see what we get. So the first bit will give me 15 pi, and then the second bit 15 over 2 multiplied by 4.8 minus 36. Okay, so there's my answer, and I'll just write down the values of A and B. So A is equal to 15 and B is equal to negative 36. So there we go, question number 1 is done. Question number 2, part A. Given that theta is small, use the small angle approximation for cos theta to show that 1 plus 4 cos theta plus 3 cos squared theta is approximately 8 minus 5 theta squared. So let's remind ourselves first of all what the small angle approximation for cos theta is, and that is, so when theta is small, cos theta is approximately 1 minus a half theta squared. And we just substitute that into here. So everywhere that we see cos theta, so cos theta there, cos theta squared, we're going to replace it with 1 minus theta squared. Right, so that will give us 1 plus 4, do the substitution, 1 minus a half theta squared, plus 3, and then 1 minus a half theta squared, and that itself is going to be squared. Let's simplify that. So I'll have 1 plus 4 minus 2 theta squared, and then plus 3 lots of this second bracket expanded. So let's do that over here. I don't want to do it incorrect. 1 minus a half theta squared times by 1 minus a half theta squared. Multiplying it out, let's see, I get 1 minus a half theta squared minus another half theta squared plus a quarter theta to the power 4. So those two are going to go together. So in my brackets I'll have 1 minus basically theta squared, because you've got minus a half minus another half, plus a quarter theta to the power 4. I made a mistake there, I put theta squared. That should have been power 4, where I've got theta squared times by theta squared. Let's simplify this. So I have 1 here, 4 here, that's 5. This is going to give me another 3, so that's going to be 8. So I've dealt with the numbers. I'll have minus 2 theta squared. Now I'm going to get another minus 3 theta squared by expanding the brackets. So I'll have minus 5 theta squared. And then I'll have 3 quarters plus 3 quarters theta to the power 4. So plus 3 quarters theta to the power 4. Now you can see it matches up apart from the last term. I've got the 8 minus 5 theta squared, that's the same. Then it's got this plus 3 quarter theta to the power 4. Now theta is small, this is probably going to be small enough to ignore. Okay, so just write down, we can ignore, because it's only approximation, 3 quarter to theta 4, since theta is small. So you imagine you've got a small number and you're doing it to the power 4, it's going to get even smaller. And then we can say, so 1 plus 4 cos theta plus 3 cos squared theta is approximately 8 minus 5 theta squared as required. Okay, let's move on to part B. Edexcel uses theta equals 5 to test the approximation in part A. Edexcel's working is shown below. So using my calculator, she substituted in 5 and got 7.962 to 3 decimal places. Using the approximation, that gives negative 117. Therefore, 4 cos theta plus 3 cos squared theta, approximately 8 minus 5 squared theta, is not true for theta equals 5. There's 2 parts to part B. It's saying, first of all, identify the mistake made by Edexcel in her working. Now, the first mistake is look at the size of these numbers. If she was working in radians, as she should have been, you wouldn't get these numbers. These are the types of numbers you would expect to get if you are working in degrees, because these numbers here represent angles. So the mistake she's made is that she has been working in degrees, or she's got a calculating degrees mode, not radians. It should be in radians. The small angle approximations are valid for radians only. And then the second part of part B, down here, and it says show that 8 minus 5 theta squared can be used to give a good approximation to 1 plus 4 cos theta plus 3 cos squared theta for an angle of size 5 degrees. So the first thing that we need to do is to convert 5 degrees into radians. Now I always use the fact that 180 degrees is equal to pi radians. I want to find 5 degrees in radians, so I just need to work out what I divide by. So let's do 180 divided by 5. So if I divide by 36, and then basically that means that 5 degrees is equal to pi over 36. So pi over 36 is what we're going to put into our approximation. Right, so putting it on the left hand side, I'll have 1 plus 4 cos pi over 36 plus 3 cos pi over 36. Now because it's cos squared, let's put a little 2 there. That means you're going to square, once you've worked out cos pi over 36, then you square it. So don't square the pi over 36. Right, and that's going to give us 7.96199, and then it carries on like that. And so we're now going to do the same thing with the other side. So using the left hand side gives 7.96 basically to 3 significant figures. Let's do the same, put the same pi over 36 into 8 minus 5, and that'll be pi over 36 squared. See what that gives us. And that gives me 7.96192. Okay, so it does give a good approximation. Now, on questions like this, it's good to say how much your answers agree to. So they agree to 1, 2, 3 decimal places, if rounded, because they will both round to 7.962. After that, they're going to round to something different. To 4 decimal places, this will round to 7.9619. This would round to 7.9, and then it will be 20. So I'll just write down here. It's a good approximation. So I'm finishing off this part C question. It's a good approximation since the answers agree to 3dp, and that number which they agree to 3dp is 7.962. Question 3. A cup of hot tea was placed on a table. At time t minutes after the cup was placed on the table, the temperature of tea in the cup in degrees Celsius is modelled by the equation theta is equal to 25 plus AE to the power negative 0.03t, where A is a constant. The temperature of the tea was 75 degrees when the cup was placed on the table, so basically at the start. And what we need to do in part A is to find a complete equation for the model. That means finding the value of the constant A. So we know when the cup was placed on the table, in other words, when T is 0, the temperature, which is given as theta, was 75 degrees. So those are going to get substituted into our equation. So that will be 75 is equal to 25 plus AE to the power 0.03 times by 0. So let's take away 25 from both sides, so we've got 50. And then what's going to happen here, we've got e to the power 0, which is just 1. Anything to the power 0 is 1. So we've got A is equal to 50. So our complete model is going to be the temperature theta is equal to 25 plus 50e to the power negative 0.03t. Part B. Use the model to find the time taken for the tea to cool from 75 degrees to 60 degrees, given your answer in minutes to 1 decimal place. Now, we know at the start it was 75, so basically we just need to work out the value of t when it's 60, and that will give us the time taken. So what we'll do in our model, we'll replace theta with 60. So that will give us 60 is equal to 25 plus 50e to the negative 0.03t. Take 25 from both sides, so we'll end up with 35 is equal to 50e to the negative 0.03t. Divide both sides by 50. So 35 divided by 50 is 7 over 10, or 0.7. So 7 over 10 is equal to e to the negative 0.03t. Then we do natural log of both sides. So that will be the natural log of 7 over 10 is equal to, so we'll do the natural log of e, that will cancel out, just leaving negative 0.03t. So that will give us t is equal to natural log of 7 over 10, or 0.7, divided by negative 0.03. Let's see what that gives us for t. Now, because we're doing a log of a decimal, this is going to be negative, so negative divided by negative, we're going to end up with a positive number. And that is, let me write it on the next line because I haven't really got enough space there. T is equal to 11.8891. Okay, we need to give the answer in minutes to one decimal place. Now, we don't need to turn this part here into seconds, so I guess it's fine if we just write an answer of t is equal to 11.9 minutes. If we did need to convert the decimal part to seconds, we will take the decimal part, the 0.8891, times it by 60, and that gives us something like 53 seconds, 11 minutes 53 seconds, but 11.9 minutes is fine. Okay, moving on to the next part here. It says 2 hours after the cup was placed on the table, the temperature of the tea was measured as 20.3 degrees. So 2 hours, and we have a temperature of 20.3. Using this information, evaluate the model explaining your reasoning. So basically what we want to do is to see, right, if we use the model and we put 2 hours in, do we get a temperature that's close to this? So let's do that first. So part C, we're going to put in 2 hours. So time is going to be 2 hours. Now, if we go back, T is measured in minutes, so we need to change that to minutes. So we need to make sure we put 120 into our model, and that then we'll work out the temperature. So the temperature, theta, is equal to 25 plus 50 e to the power negative 0.03 times 120. Let's see what this gives us for the temperature. And that gives a temperature of 26.36 and so on degrees. Now I can see that this answer is off by about 6 degrees from what the actual temperature was, and there's a reason for that. If we look at our model, we've got 25 and we're adding something to it. Now what we're adding to it is going to be a number that's getting smaller and smaller, but it's always going to be a positive. This model, doesn't matter how much time you put in, is never going to go below 25 degrees, and we've got a temperature of 20.3. So really this model only works, or is never going to give a temperature below 25 degrees, which we have seen. Okay, so we can either say that this temperature that we worked out here is not approximately 20.3, or we can talk about the model. So we can say, so this is one answer we could give. Another one is that the model only will give, not very good English is it, will give a temperature, or a minimum temperature, of 25 for large values of t, or just above 25. As t gets bigger, the temperature is going to get closer to 25. Question 4. What we need to do in part A is sketch the graph with this equation. Y is equal to the modulus of 2x minus 5. Right, so just a reminder of the modulus transformation. So if you've got a modulus around the whole function, you reflect anything that's below the x-axis, the graph, you reflect it up. And if the modulus is just around the x, then you take the graph which is on the positive x side and you reflect it to the negative x side. So we've got the first type here. So we're going to draw the graph or a sketch of it, and anything which is below the axis we're going to reflect up. So let's just draw an axis over here. So because it's a sketch, you're just going to want to get the right shape and also mark any points where it's on the axis. And let's make sure we label the axis correctly. So x and y. So I know this is going to be a straight line. So I start by drawing the line y is equal to 2x minus 5. So it's going to be a line with a positive gradient. So let's start with that. Y is equal to 2x minus 5. I want to see where it crosses the x and the y axis. So if I make x equal to 0, that will give me negative 5. So across the y-axis at negative 5. So I'm just going to put a mark there, minus 5. And if I make y equal to 0, that will give me 2x is equal to 5, which will become x is equal to 2x is equal to 5. X is equal to 5 over 2. So that line is going to cross the axis at 5 over 2 x value. Right, so the original line, the line of y equals 2x minus 5, is going to look like this. Now what we do is we take the part of the graph which is down here and reflect it up. Now when it gets reflected up, it's going to cross at positive 5. So what I will do is to put positive 5 here, and then my graph is going to look like this. So it goes down and then it's going to bounce back up and finish there like that. And so I take out the original line there, and there we go. There's our sketch of the graph of y is equal to the modulus of 2x minus 5. Okay, part B of this question. It says we need to find the values of x which satisfy the modulus of 2x minus 5 is greater than 7. So to solve these types of equations, we need to replace the modulus with brackets and a plus sign and brackets and a minus sign. So let's do that. So I'll have 2x minus 5. So you replace the modulus with brackets and a plus sign. So I want to solve this is greater than 7. So that will give me 2x minus 5 is greater than 7. We will add 5 to both sides, so 2x is greater than 12, and that leaves me with x is greater than 6 as one part of my solution. So let's write that down. Then what I do is replace the modulus with a minus and brackets, so negative brackets 2x minus 5 is greater than 7. Then what I want to do, if I multiply both sides by negative 1, so I'll get 2x minus 5 is less than negative 7. Remember, flip the sign when you multiply or divide by a negative number. Then we will add 5 to both sides, so 2x is less than negative 2. Divide both sides by 2, so we got x is less than negative 1. Okay, so there's the other part of my answer. Now if you wanted, you could leave your answer in set notation. So this is what it would look like if the question did ask for set notation. I always struggle to draw these curly brackets. Look how bad they are. Right, part C. We need to find the values of x which satisfy this equation here. And this does ask us to write our answers in set notation. So the first thing we want to do is to find out where these intersect. So we'll need to solve 2x minus 5 is equal to x minus 5 over 2. And we also want to solve negative 2x minus 5. is equal to x minus 5 over 2. So let's solve the first one. So that will be 2x, and let's take away x from both sides. So I'll have x, and then I'll add 5 to both sides. So that will be negative 5 over 2, which is like negative 2.5, and add 5. So I'll have x is equal to 5 over 2, or 2.5. We'll do the same here. We'll solve this. So I'll get negative 2x here. And then if I add 2x to both sides, so negative 2x, add 2x to both sides, I'll get 3x is equal to, so that's negative 2x, put it over here, I get 3x. And then I've got negative 5 over 2, I'm going to put it over here, so negative 5. So I've got 5 plus 5 over 2, and that gives 15 over 2. And then divide both sides by 3. So I also get x is 5 over 2. I get the same value. Now that means that these two graphs only meet at one point, and that point is the coordinate. Basically with its coordinate is 5 over 2. So it's got 5 over 2, 0. And that's this point here. So I'm now going to sketch on the other line. So the other line, the x minus 5 over 2 is going to look like this. So it's only touching at that point, and it's crossing this axis here. Its y-intercept is minus 5 over 2, so we'll put that on minus 5 over 2. Now we need to solve an inequality, and we can think of this inequality as, when is the modulus graph, the modulus of 2x minus 5, when is that greater or above the graph of x minus 5 over 2? So looking at our sketch here, the modulus graph is this one. Can you see it's above it everywhere apart from the point where they meet, because it's not above it at that point. So everywhere except the point where they meet there. And we need to write that in set notation. So our solution is going to be this, that x, so we always write x colon, and then we write what our condition is. X is, or that graph is above the other one everywhere. That's what that bit means. And then we put a a comma, we're going to put a condition, except where x is equal to 5 over 2. So what I've got in set notation here is that my variable is x. This the solution to this is for all values of x, comma, except where x is 5 over 2. So that will be my solution for this question. Question 5. The line L has equation 3x minus 2y is k, where k is a real constant. Given that the line L intersects the curve with equation y is equal to 2x squared minus 5 at two distinct points, let's put that in, at two distinct points, find a range of possible values for k. So this type of question is about putting these two together and using this discriminant. So let's do that first. Put them together. So I need to make y the subject or x the subject of that first equation that I've got, y minus 2, 3x minus 2y is k. Right, I think I will make y the subject. So if I do that, I'll have 2y is equal to 3x minus k, divide both sides by 2, and I'll get y is equal to 3 over 2x minus k over 2. That's going to get substituted into the second equation here. So y becomes 3 over 2x minus k over 2 is equal to 2x squared minus 5. That's a quadratic, so we'll bring everything to one side. So you've got 2x squared, and then minus 3 over 2x, and then my constant is going to be plus k over 2 minus 5. So I'll just put that in brackets there. Here I use the discriminant, b squared minus 4ac. Now since it said there are two distinct roots, that discriminant is going to be positive. That means I'm going to be substituting a value of a as 2, a value of b as negative 3 over 2, and a value of c as k over 2 minus 5. Let's do that and see what we get. So b squared, so minus 3 over 2 squared is my b squared, minus 4 times a, which is 2, times by c, which is k over 2 minus 5. And that's going to be greater than 0. Right, let's tidy that up. So we'll have b squared, sorry I forgot the square root sign, so that'll be 9 over 4, and then minus 8 times by that k over 2 minus 5 is greater than 0. So from there, 9 over 4 minus 4k plus 40 is greater than 0. So what we want to do is to make k the subject. So let's have 4k. Let's bring that to the other side. And if we do that, then it will be less than 9 over 4 plus 40. So we'll divide both sides by 4 and we will get k is less than, let's see what that is, 40 plus 9 over 4, 40 plus 9 over 4, and then we're going to divide that by 4, so that's 169 over 4 divided by 4 gives me 169 over 16. So the range of values is that k needs to be less than 169 over 16 for this curve and line to cross in two places. Question 6. Figure 2 shows the sketch of a curve with equation y equals f of x, where f of x is equal to 8 minus x log x. X is greater than 0. The curve cuts the x-axis at the points A and B, which are here, A and B, and has a maximum turning point at Q as shown in figure 2. So we've got a maximum at this point here at the top. What we need to do in part A is find the x-coordinate of A and the x-coordinate of B. When we find these coordinates, we are finding the roots, because these x-coordinates are the points where the graph crosses the axis, so they're roots. So that means f of x is equal to 0. So we set our equation 8 minus x log x equal to 0 and solve for x. So from this, either 8 minus x is 0 or log x is 0. So let's start with the 8 minus x equal to 0. That's nice and easy. That means that x is 8. And then we'll go with the log x is equal to 0. Now you should know that log of 1 is equal to 0. If you didn't know that, what you would do e to both sides. Then the e and the log will cancel out, giving you x is equal to e to the power 0, which is 1. But it's useful to know that log 1 is 0, so x is 1. Now we need to give the answers as coordinates, and we need to give them the right way around. A has to be the smaller of these two, so A has to have an x-coordinate of 1, so that's going to be 1, 0, and B has to be the one which is 8, is further across, 8, 0. Okay, moving on to part B. Show that the x-coordinate of Q satisfies this equation here. Okay, now since we have Q is a maximum point, that means that the derivative is 0, so f dash of x is 0 at Q, at this maximum. So we're going to have to differentiate what we've got here. So since I've got a product, I'm going to use the product rule. I will set u as 8 minus x and v as log x. That means du dx, or u dash, is negative 1, and dv dx, or v dash, is 1 over x. So using the product rule, it's going to be these two times together. So that's going to be 8 minus x times by 1 over x plus u dash v, so that's going to be negative 1 times by log x, so it's basically minus log x. So I'll change that to minus log x. Okay, and we need to set that equal to 0. So you've got 8 minus x times by 1 over x minus log x is equal to 0. Right, and basically we just need to rearrange it to get into this form. So the first thing I'm going to do is to move the log x to the other side. So I've got 1 over x, 8 minus x is equal to log x. Then I'll expand the brackets. So I'll have 8 over x minus 1 is equal to log x. Then I will add 1 to both sides. So I'll have 8 over x is equal to log x plus 1. Then I'm going to do the reciprocal to both sides because I've got this x at the bottom. So let's just flip over both sides. So I'll have x over 8 is equal to 1 over 1 plus log x, or log x plus 1. So I'm just keeping an eye on this and getting it in that form there. So swapping that around so it matches up with that. Always get your answers to match up exactly with the form that they want. Then the next step, times both sides by x. X is equal to 8 over 1 plus log x as required. So we've got it in the form that they want for parts B. Part C says we need to show that the x coordinate of Q lies between 3.5 and 3.6. So Q is this maximum point. So if I knew the exact x coordinate of Q, then f dash of x would be 0 because it's that maximum point. So what I'm going to do is I'm going to work out f dash of 3.5 and f dash of 6. Let's do that. So part C, f dash of 3.5, so that means that we do 8 minus 3.5 times by 1 over 3.5 minus log 3.5, and that gives me 0.032951 and so on. Now I'm going to work out f dash of 3.6. So 8 minus 3.6 times 1 over 3.6 minus log 3.6. And I get negative 0.058711 and so on. So what this piece of information is telling me is that between 3.5 and 3.6, or at 3.5 the gradient's positive, at 3.6 the gradient is negative. So somewhere in between the gradient is 0. So we always need to finish this off with some sort of conclusion statement, and it needs to include the phrase change of sign. So we'll write something like this: since, in the right colour, so since there is a change of sign, that's important that you have that, there is a change of sign from f dash of 3.5 to f dash of 3.6, the x coordinate of Q lies between 3.5 and 3.6. So we're basically just copying what they've done there. It lies between 3.5 and 3.6. Part D, use the iterative formula, and this iterative formula is based on what we worked out in part B. With x1 equal to 3.5, what we need to do is find the value of x5 to 4 decimal places. So we're starting x1 is equal to 3.5. So 3.5 is going to go into our iterative formula. x2 is going to equal 8 over 1 plus natural log 3.5. So that's going to give me 3.5511 and so on. Now the way that we do this question, remember, we're not going to work out each one individually. Remember, you start by doing 3.5 equals, so it's stored on your answer button. Then we're going to press the fraction button and we're going to do 8 at the top of the fraction, and then at the bottom of the fraction we are going to do 1 plus natural log, and you press the answer button, close brackets, and you just got to keep pressing equals. So if I do that, then I get all the rest of the answers just by pressing equals. So x3 is 3.5284 and so on. Press equals again. X4 is 3.53847 and so on. And then x5, this is the one that I want, so I press equals one more time and I get 3.534 and so on. I want to give that to 4 decimal places, so x5 is going to be 3.53, and then it goes 404, so it would just be 40. Okay, and we're now ready to move on to the last bit. Let's just highlight that answer, and that's the second part of part D. And then it says what we need to do is to find the x coordinate of Q accurate to 2 decimal places. Now what you do here, you're going to keep pressing the equals button until you don't see a change or you see the numbers are the same to 2 decimal places. And I'm getting something like, I've just pressed it lots and lots of times, and I'm getting 3.535401.036. I'll round that to 2 decimal places, so that's going to be 3.54. So 3.54 is going to be my answer here to 2 decimal places. Question 7. A bacterial culture has area p millimeters squared at time t hours. So the time is measured using hours, and at t after the culture was placed on a circular dish. A scientist states that at time t hours, the rate of increase of the area of the culture, so that's the rate of increase of the area over time of the culture, can be modelled as being proportional to the area of the culture. Show that the scientist's model for P leads to this equation here. P is equal to AE to the power KT. So we need to translate that maths talk into an equation. So the first thing, we are talking about the rate increase of area over the time. Now for area we're using the letter P, so it's dP over dt. As soon as you see rate of something, you're thinking d something over d something, and that's going to be equal to being proportional to, so K, the area, which is P. So there's our start. Right, what we do here is we're going to solve this first order differential equation by separation of variables. That means collecting the like terms, putting all the p terms on one side and then the t terms on the other. So if I divide both sides by p, I'll get 1 over p dp, and then if I keep the k on the other side and then times both sides by t, I get this. So you can see there are no t terms, so just leave the constant there. Now I could have also taken the constant over the other side and had 1 over kp. I would get an equivalent answer, but I've decided to keep the constant there. Then we integrate both sides. So the left hand side is going to be integrated with respect to p. So 1 over p integrated becomes log p, natural log p. Then on the other side, k integrated with respect to t becomes kt plus c. Now we only need to put one constant in, even though we're integrating both sides. The constant on the left and the constant on the right we put together to become a single constant. The next step is we're going to do e to both sides because we want to make p the subject. So I'll do e, and then each side is going to become the power. What will happen is that e and the log p will cancel out, giving me p is equal to e to the kt plus c. I can use the rules of powers here on the right hand side to write that as p is equal to e to the kt times by e to the c. Now e to the c, this is a constant. I'm doing e to a constant value, so that's a constant. So I'm just going to put here let a equal e to the c. It's just a constant, and I'm using a because that's what they've used in the question. And then my final result is going to be p is equal to a, that's the e to the c, times by e to the kt, as required. Moving on to part B, it says this: the scientist measures the values for P at regular intervals during the first 24 hours after the culture was placed onto the dish. She plots a graph of log P against T and finds the points on the graph lie close to a straight line with gradient 0.14 and vertical intercept 3.95. What we need to do is to estimate to two significant figures the value of A and the value of K. So because we're talking about a linear model, we need to go back to where our exponential model looks linear, and that's up here. Let me just highlight that. So at this point, this looked linear, didn't it? Looks like the equation of a straight line. So that's log P is equal to kt plus c. Now if I was to match that up with the equation of a straight line, the log P looks like y, the k would be like the gradient, x would be like the t, and then the c would be the intercept. So what does that mean? I can match this up, and the gradient of 0.4t would be equal to k. So I'm right, k is equal to 0.14 because that matches up with the gradient. And the intercept matches up with c. So c is equal to 3.95. But we need to find a. Now remember up here we said that a is equal to e to the power c. So a is equal to e to the power 3.95. And that evaluated, worked out on a calculator, is 51.93536 and so on. Now we need to give those values, both of them, to two significant figures. So I've got the value of k to two significant figures, so let's highlight that. I now want to give the value of a to two significant figures, so that would be 52, rounding this to two significant figures. So there's my value of a. Moving on to part C, and that says, hence show that the model for P can be written like this: P is equal to A times B to the power T. So what I've got so far is P, if I go back to the model that I've got for part A, P is equal to A, which is 52, times by E to the power KT, so that's 0.14T. And then from this, I just need to match up, I need to find the value of the constant B. The constant B matches up with the E to the power of 0.14, because that part here, remember you can write this as E to the power of 0.14 times by, or to the power of T, because you'd multiply those powers, which is what we've got here, multiplying powers. So we're going to work out what E to the power 0.14 is. So B is equal to that, and that gives me on my calculator 1.15, and that's given to three significant figures as they've asked for. So the final part of my model would be P is equal to A times by 1.15 to the power T, but they basically asked for the value of B, which we've got here, 1.15. Part D. With reference to this model, that's this model here, first part of part D is to interpret the value of the constant A. Now the constant A matches up with 52. So A is 52. Now, when are we going to be using that 52? When are we going to get maybe just 52 on its own? That's when T is 0. So when T is 0, what you'll get is a population, sorry, an area. Keep seeing P for population, so it's area. The area is 52, and I think it's millimeters squared, something like that. Okay, now we can interpret it. So this is not an interpretation. An interpretation is going to use the words area and time. And so we'll say something like 52 is the area of the bacteria at the start, or initially, or the beginning. So bacteria, I'll just put initially, that's the start. Second part of part D, interpret the value of the constant B. So B is the 1.15. Now, when is the 1.15 going to come into play? Well, every time I times by t, or increase t, so every time I increase t by 1, I'm going to be multiplying by 1.15. The population is going to get multiplied, or the 52 is going to get multiplied by 1.15 as each hour increases. Now, if I'm multiplying by 1.15, that's the same as an increase of 15%. Increase of 15%. So now we can interpret it, and we can say something like that the population increases by 15% each hour. Not the population, the area. So the area increases. So I really shouldn't have used P for area. It's getting me confused. The area increases by 15% each or every hour. So something similar to that. Part E. State a long-term limitation of the model for P. So one limitation is that this model assumes the bacteria are just going to keep on increasing. In real life, that's not going to happen. So I could write down that long-term, the model predicts that the population will keep on increasing forever, will keep on increasing forever. Now, it can't do that. I guess one reason it can't do that is because, like, you know, the circular dish only has a certain size, and when it's full, it's full. The bacteria can't keep on increasing. So let's see. Long term, the model predicts that the population will keep on increasing. This is not possible as the circular dish has a finite area. So some sort of description like that would be fine. Question 8. A bowl is modelled as a hemispherical shell as shown in figure 3. Initially the bowl is empty and water begins to flow into the bowl. When the depth of water is h centimetres, the volume of water V, according to the model, is given by V is equal to 1/3 pi h squared and then 75 minus h in brackets for h between 0 and 24. The flow of water into the bowl is at a constant rate of 160 pi centimetres cubed per second for h when it's between 0 and 12. Part A, find a rate of change of the depth of water in centimetres per second when h is 0. So we're actually trying to find the rate of change in the depth of water in centimetres per second. So we're trying to find rate of change is d something, okay. What's the top bit going to be? Well, we can look at the units here. So if it's centimetres, that's the height, the change in height or depth of water over time. You've literally got here centimetres over s. It's the same thing. So dh dt, the change in the depth of water over time, that's what we're trying to find. Now, we can't find that directly, but there are some other things we can use to help us find that. So the first thing we're going to look at is this. We've been given that V is equal to 1/3 pi h squared 75 minus h. Now I'll expand the brackets of that and I'll get 75 over 3, so that's 25 pi h squared minus 1/3 pi h cubed. And I'm going to differentiate this with respect to h and find dv dh. So if I do that, the 25 pi h squared will become 50 pi h, and then the 1/3 pi h cubed is going to become minus pi h squared. Then I'm going to look at this next bit of information. The flow of water into the bowl is at a constant rate of 160 pi, and that's centimeters cubed per second. Again, I've got some units here. So look, that's a volume over a time. So what I've got from that is dV dt. And dV dt, because it's flowing into the bowl, it's increasing, so it's going to be positive. And dV dt is just 160 pi. So I want to find dV dh. I want to find dH dt. I've got dV dh, and I've got dV dt. These two can be multiplied together, maybe if I use some reciprocals to do that. So dH dt is equal to dH dV, so the reciprocal of this thing here, just flip it over, times by dV dt. Let's improve that h, it looks like something different. Okay, now what's going to happen? Well, the dV's will cancel out, and that will give me dH dt. So dH dt is going to be equal to basically 1 over this times by this. So I can write it as 160 pi over 50 pi h minus pi h squared. And then what I can do is I can cancel out the pi's. So I'll have 160 over 50h minus h squared. Next step, now that I've found dH dt, is substituting this h is equal to 10. So that's going to go in there. So that will give dH dt is equal to 160 over 50 times 10 minus 10 squared. So that's going to be 160 over 400. And that is 0.4, and I'll stick the units on the end. So that's centimeters per second. Okay. Part B, find the rate of change when the depth of water in centimeters cubed is h is equals 20. And what changed in part B, it says that given that the flow of water into the bowl is increased to a constant rate of 300 centimeters cubed per second. Now, before that was 160, so we've now changed it to 300, and we want to work out the rate of change when h is 20. So we don't need to go through this whole process again. We just need to look at what would change. Now it was, let's highlight it, 160, and that is here. Whoops, don't want to draw over it, just highlight it. So that's what it was, 160. Now where did that 160 end up? It ended up here, 160 pi, and then it ended up as 160, and then we ended up substituting. So let's use this bit and just change that 160 pi to 300 pi. So we would have dH dt now is going to be 300 pi over 50 pi h minus pi h squared. Again, we can take all the pi's out, and we end up with, sounds like I'm going to go to the refrigerator and take the pi's out. So 300 over 50h minus h squared. So now I'm just going to substitute in h is 20 now instead. So dH dt is going to be 300 over 50 times 20 now minus 20 squared, and that changes the answer to 0.5 centimeters per second. Question 9. A circle with centre A, which is 3, -1, passes through the point P, -9, 8, and the point Q, 15, -10. What we need to do in part A is show that PQ is a diameter of a circle. Now, if PQ is a diameter of a circle, then the centre of the circle will be at the midpoint of PQ, because it'll be in the very centre. It's in the centre of the circle. So what we're going to show is if A is the midpoint of PQ. So let's work that out first. So the midpoint of PQ. So we add the x coordinates together, divide by 2. We add the y coordinates together, we divide by 2, and that will give us -9 plus 15, which is 6. So we've got 6 over 2, and then 8 minus 10 is minus 2, so you've got minus 2 over 2. That simplifies to 3 minus 1. So we need to give a reason why. Don't just sort of do that. So we'll say that since A is the midpoint of the line segment PQ, therefore, it follows that PQ is a diameter of a circle, of the circle. Right, part B. It now says find an equation for a circle, for the circle. Now, if I want the equation, I need two things, the centre and its radius. So I have the centre already, that's A, that's 3, -1. What I need now is the radius. Now, to find the radius, what I can do is take the distance between P and A, or Q and A. I'm going to find a distance between the points P and A, or A and P. That will give me the radius. So that's going to be the square root of the difference between the x coordinates. So I've got the difference between those is going to be 3 minus -9, all squared. Then the difference between the x coordinates, that's going to be -1 minus 8, all squared. That's going to be the square root of 12 squared plus, that's going to be -9 squared. And that gives exactly 15. So the equation for the circle is going to be x minus 3, all squared, plus y plus 1, all squared, is equal to 15 squared. Let's move on to part C. Now it says here that we have a point R lies on a circle. Given that the length of the chord PR is 20 units, what we need to do is to find the length of the shortest distance from A to the chord PR. So I'm just going to draw like a little sketch of a circle here. I'm going to put these points on. So I have P here, Q is opposite. That forms the diameter, A is in the middle, and then I've got this point R, which is somewhere else, so I can put it anywhere. So I'll just put this point here, R. I'm looking at the chord that goes between P and R, like this, and I want to find the shortest distance, and that's always the perpendicular distance between a point and a line. That gives the shortest distance. Now I know that the length of this here is 20. I know that when a radius meets a chord, it bisects that chord. So these two halves are going to be the same length. In other words, each half is going to be 10. And my job now is to work out what's the length of this bit here. Now I could actually zoom in a bit so that we can actually see what's going on here. Oh, actually, let me just highlight it maybe in a different colour, like this. I've basically got here, look, a right angle triangle. See that? Let me draw the right angle triangle like this. Now, the right angle there is going to be this right angle down here. The length of this side here, that's 10, so that's going to go on this side of my diagram, 10. And the length of this side, well, that's just the radius of the circle, 15. I want to find the shortest distance, that's this length here, which is this length down here. That's going to be my shortest distance, so it's just Pythagoras. So that's going to be the square root of 15 squared minus 10 squared. And that gives exactly 5 root 5. Moving on to part D. In part D, what it says here is that we need to find the size of the angle ARQ, giving your answer to the nearest 0.1 of a degree. Okay, so let me just take that out for the time being and just take out the bits that we don't need. Okay, so angle ARQ, let me just draw that on, is going to be something like this. So ARQ. So I want to find this angle here. Now I'll draw it in a thinner line because I'm going to have to put some other things on here so you can see what's going on. Right, so ARQ, that's this angle here. Okay, now if I draw this line in here, actually if I draw the diameter in, then this part of the triangle here, this is an isosceles triangle, isn't it? Because these are the two radii. So this angle is the same. So if I can find this angle, I found ARQ. Now can I find this angle? Yes, I can. If I look at the big triangle here, then I can use some trigonometry to find this angle here, which is going to be the same as that one. So let me draw my right angle triangle out. So this is the one that I've got highlighted in yellow, and it's going to look something like this. So this side here is the diameter. So I know that the radius is 15, so the diameter is 30. So that's that length there, that's the hypotenuse of my triangle. And the length of this side here is 20. And I want to find this angle down here, so this one. That should be easy enough. I can see that I've got a hypotenuse and an opposite. So the sine of that angle, so the sine of a angle ARQ, sine of angle ARQ, actually the sine of this angle AQR, but it's the same size. Actually, let me write that first. That angle ARQ is equal to angle AQR, and that's because we've got an isosceles triangle there. So it makes sense. So now when I say I'm working out the sine of AQR, I know I'm working out the sine of ARQ, and that's going to be equal to the opposite, 20 over the hypotenuse, 30. And doing sine inverse, that gives me that angle ARQ equal to 41.8103. They want the answer to the nearest 0.1 of a degree, so that's going to be 41.8 degrees. Question 10. Figure 4 shows a sketch of a curve C with parametric equations. X is equal to log t plus 2 and y is equal to 1 over t plus 1, where t is greater than negative 2/3. Part A, state the domain of values of x for the curve C. Now if we're trying to find the domain of a parametric function, it's going to be the x part of the parametric function that's going to give us the domain, because the x is like the input values, the domain is the input values. So we need to look at this, and we need to look at the value of t. that's going into this, that's going to help us find what I'm going to call the edge of the domain. Where does the domain start or finish? So t needs to be greater than negative 2/3. So to find the edge of the domain, I'm going to replace this t here with negative 2/3. So I've got x is equal to log negative 2/3 plus 2. That's going to give me natural log of 4/3. That's where the domain either starts or finishes. How am I going to know where the domain goes? Well, since t is going to be greater than negative 2/3, that means that this bit in brackets here, the 2/3, I'm going to get a number that's greater than 4/3. So that means that the domain, the input values, the x values, are going to be greater than log 4/3. The edge of the domain is log 4/3, but since t needs to be greater than negative 2/3, this value here is going to be greater than log 4/3. So that gives us our domain. So that's part A. Part B. The finite region R, shown shaded in figure 4, which is here, is bounded by the curve at the top, the line with equation x equals log 2, which is on the left hand side, and a line with equation x equals log 4 on the right hand side, and the x-axis at the bottom. Use calculus to show that the area of R is log 3/2. Now any question here that tells you to use calculus either means that you're going to differentiate or integrate to find your solution. We know that if we're going to find the area of something, we're going to integrate it. It won't say integrate, it will just say calculus. You need to know what calculus is. Since I have a parametric equation, I'm going to use the formula for parametric differentiation, which is y dx dt, where the limits are t limits. I'll call them t1 and t2. Now there are other ways of doing this. I can put these two together and eliminate t and integrate that function with respect to x, but I prefer to do this one. It's just a preference, you can do it either way. So let's start with the limits here. Now the limits at the moment of this are x limits. They need to be changed to t limits. How am I going to do that? I'm going to use this. This will take x's and turn them into t's. So let's do our working over here. Limits. So I have x limits of log 2 and log 4. And let me change those limits into t limits. Now if x is log 2, that means that the value of t over here needs to be 0. So that's one limit. If x is log 4, this value of t here needs to be 2. So make that 2. So now I have my parametric limits. Now we need to make sure we use them the right way around. So log 2 would be at the bottom, log 4 would be at the top. So log 2, which is 0, needs to be at the bottom, and log 4, which is 2, needs to be at the top. Now, even if these values, let's say the original value had the smallest value at the bottom of the integral, and it gave you a bigger value, don't swap them over. Always match them up. Log 2 goes with 0, log 4 goes with 2. So even if this number here was bigger from the log 2 value, don't write it at the top, so don't swap them over. Keep them that way around. Then I'm going to write down y, which is 1 over t plus 1. And that's going to be multiplied by dx dt. So now I need to differentiate this. Okay, so I've got x is equal to natural log t plus 1. So I'm going to work out dx dt using a rule of logs. That basically means it's going to be, or not the rules of logs, but the rule for differentiating log of a function, it's that function differentiated over itself. So t plus 1 that function differentiated over itself. So it's going to be 1 over t plus 2. There's my dx dt. So that's going to go into the second brackets. 1 over t plus 2. And this all needs to be integrated with respect to t. Now, when I see something like this, I can see it's going to be partial fractions to integrate, because I can put those two together and I'll get 1 over t plus 1 times by t plus 2. So I've got these factors here, t plus 1 and t plus 2, and I'm going to use partial fractions. So I'll just write down here partial fractions so you know what I'm doing. Partial fractions. Okay, so I'm now going to set up my partial fraction and work it out. Let's do it in blue. So 1 over t plus 1 times by t plus 2 is going to be equivalent to a over t plus 1 plus b over t plus 2. If I make the denominators the same, then the numerators I can equate to each other. So I'll have 1 is equal to a times by t plus 2 plus b times by t plus 1. Let's work out the values of a and b. So if I make t equal to negative 2, what will happen is this will disappear and I will have 1 is equal to, so I'm putting a negative 2 here, I'll get negative 1, so 1 is equal to negative b, which means b is equal to negative 1. Okay, now I'll make t equal to negative 1. That's going to allow this part to disappear. So if I put negative 1 here, negative 1 plus 2 is 1. So I'll end up with 1 equals a, or a equals 1. So I'll just write that up here, a, because I'm going to rub this out in a moment. A equals 1, b equals negative 1. And then I can write down my partial fraction, which I can integrate. So I now have integral between 0 and 2 of a over t plus 1, so that's 1 over t plus 1. B is negative 1, so it's minus b, not b, it's minus 1 over t plus 2. I'm going to integrate that with respect to t. Now we're ready to integrate. So the bottom differentiated becomes the top. So this is log of the bottom, so log of t plus 1 minus, the same with the second partial fraction here, the bottom differentiated becomes the top, so it becomes natural log t plus 2, and this is between the limits of 0 and 2. Okay, let's put in that bracket first. Let's now substitute in the 2 and the 1. So if I do that, this first term here becomes log 3, so natural log 3 minus, and then the second term here is going to become log 4. Log 4, that's the first one, and then minus, now we're going to put the 0 in, so the first term becomes log 1, natural log 1, which is 0, and then minus log, natural log 2. So this will become log 3 minus log 4, the log 1 disappears because it's 0, and then minus log 2, so plus log 2. All of these logs can be put together, so I'll end up with the natural log of the log 4 plus the log 2. That's going to be multiplied, but that's all going to get subtracted from the log 3. That means divide, so I'll get log 3 divided by log 4 times by log 2. So that becomes natural log of 6 over 4, which becomes natural log 3 over 2. Okay, which is what they want. So we've got that as required. Question number 11. The second, third and fourth terms of an arithmetic sequence are 2k, 5k minus 10 and 7 minus k, respectively, where k is constant. Show that the sum of the first n terms of the sequence is a square number. Okay, so we have the second term, which is 2k. We don't have the first term. The third term, which is 5k minus 10, and we have the fourth term, which is 7k minus 14. This is to do with an arithmetic sequence. So I'll write down the formula for the sum of an arithmetic sequence, which is this. So we've got n over 2, we've got 2a plus n minus 1d, and that's all times by n over 2. Okay, so that's the formula I'm going to use. So n is just going to be n because it's n terms, but I need to know the first term and I need to know what the common difference is. So we've got these terms here. Now the difference between any two consecutive terms is always the common difference. So if I do the third term and subtract the second term, I get the common difference. Now if I do that, I get 3k minus 10. If I do the same with the fourth term and I subtract the third term, that will also give me an expression for the common difference. So if I do that, that gives me 2k minus 4. So minus 14 plus 10, 2k minus 4. Right, these two values are equal to each other because they both give the common difference. So we'll just write down that 3k minus 10 is equal to 2k minus 4. Right, we can solve that. Take away 2k from both sides. Add 10 to both sides. So k is 6. Okay, now I know what the value of k is. I can now work out what these terms are. So the first term is 2k, which is 2 times 6, which is 12. The second term is 5k minus 10. That's 5 times 6 minus 10. And that is 20. The third term is going to be 7k minus 14. So that's 7 times 6 minus 14, which is 28. Right, so I have the first term 12, second term 20, third term 28. Right, I can see from this that the common difference is 8. It goes up in 8s. I can also see, since it goes up in 8, that the first term must be 4. So a is 4. Now I can put these into the formula. So the sum of my n terms is n over 2, 2a, so 2 times 4, plus n minus 1 times by d, which is 8. Let's see what we get when we simplify this. So we'll have n over 2 times by 8 plus, let's expand the brackets, 8n minus 8. Right, so the 8's will cancel out here. That just leaves n over 2 times by 8n. And if we do that, that gives us 4n squared. Right, now is this a squared number? Where anything squared is a squared number. And this is the same as 2n all squared. And I can just write down here and finish it off that 2n all squared is a square number. Anything squared is a square number as required. As required. Question 12. A curve C is given by this equation, sin x plus cos y is equal to 0.5, and we've got some limits here for x and y. A point P lies on C. The tangent to C at the point P is parallel to the x-axis. Find the exact coordinates of all possible points P, so I'm expecting more than one answer, justifying your answer. So because I'm talking about tangents, or if it was normals, we need to differentiate. So I'm going to take this and differentiate it. Because it's got a mixture of x and y, it's going to be implicit differentiation. So sin x becomes cos x. Cos y is going to become minus sin y dy dx. 0.5 differentiate with respect to x becomes 0. I'll rearrange it to make dy dx the subject. So I'll start by doing cos x is equal to sine y dy dx. And that will give me dy dx is equal to cos x over sine x. Or sine y, sorry. Now, since this tangent is parallel to the x-axis, so since the tangent is parallel to the x-axis, that means that this is a line that goes straight across. That means that dy dx is 0. Now if dy dx is 0, that means that the top part of this is 0. That means that cos x is 0. Okay, let's find out what those values are. So here's a quick sketch of cos x. Now our values of x need to go only between negative pi over 2 and 3 pi over 2. So let's do that. So my graph's going to look something like this, where I have negative pi over 2 here, and then pi over 2 here, and then 3 pi over 2 here. When is cos x equal to 0? Well, it's equal to 0 at these 2 points. So that gives me x is equal to either plus or minus pi over 2. So this gives me my x coordinates. I now need to work out the y coordinates, so I go back to the original equation over here. So let's start with the x is equal to the positive pi over 2. So if I substitute that in, I'll get sine pi over 2. Now I'll rearrange it, so I'll move the 0.5 over, and that's going to be equal to negative cos y. So sine pi over 2, that's 1, so 1 minus 0.5, that's a half, or 0.5. So I've got a half is equal to negative cos y. In other words, cos y is equal to negative a half. Cos y is equal to negative a half. Now if I do the cos inverse of negative a half, that gives me 2 pi over 3, or 2/3 pi. Now I need to check whether there are other solutions, so I'm going to draw a sketch of the graph of cos y. Now my graph of cos y needs to go only between negative pi and positive pi. So that's going to look like this. So up to positive pi and down to negative pi. Okay, so negative pi here, positive pi here. I could use a cast iron theorem as well to solve this. So 2 pi over 3, maybe that's going to be something like this. So there's going to be another solution over here. Might be easier with a cast diagram actually. So that's going to be negative at 2 pi over 3, or 2/3 pi. So let me write down the coordinates that I've got so far. So I've got, using the plus pi over 2, I've got a y coordinate of 2 pi over 3, and I've got another coordinate pi over 2 this time, but negative 2 pi over 3. Now let's substitute in the other value for x. So x is equal to negative pi over 2. So that will give us sine negative pi over 2 minus 0.5 is equal to negative cos y. So from this, the sine of negative pi over 2, that's going to be negative 1 minus 0.5. So we end up with negative 1.5 on this side is equal to negative cos y. In other words, cos y is equal to 1.5. Now there are no solutions for that. The graph doesn't go up to 1.5, it only goes up to 1. So there are no solutions from that. So in fact, the only 2 coordinates are the ones that we found already here. Question 13, part A. Show that cosec 2x plus cot 2x is equivalent to cot x. Whenever you've got any type of identity, always start with a more complicated side and simplify it. So we're going to start with that cosec 2x plus the cot 2x. Now, I don't really fancy using like the double angle for tan and doing 1 over that, or trying to do a double angle for cosec. So my first step would be to change these into sine and cos. So cosec is the reciprocal of sine, so I can write that as 1 over sine 2x. Cot is the reciprocal to tan, so it's cos over sine. Now can you see these are both over the same denominator, which means they can both be put together. So I have 1 plus cos 2x is over sine 2x. It's now at this point that I would use the double angle formulas. So at the bottom, sine 2x is 2 sine x cos x. And then at the top it's going to be 1 plus, now the double angle for for cos 2x, I've got 3 choices. I could either use cos squared x minus sine squared x, or I could use 2 cos squared x minus 1, or I could use 1 minus 2 sine squared x. Let's have a think about which one would be more useful. See, I've got this one there. I can get rid of the 1 by using this identity here because I've got a negative 1. So that seems like a sensible choice. So we've got 2 cos squared x minus 1. So the 1's are going to cancel out. So we have 2 cos squared x over 2 sine x cos x. Now what's going to happen here? The 2's will cancel out. The cos will cancel out with the cos squared, and that just leaves me with cos x over sine x. And what is cos x over sine x? That is equivalent to cot x. So we've proved that identity. Part B. Hence or otherwise, solve for theta between 0 and 180 this equation here. So we've got cosec 4 theta plus 10 plus cot 4 theta plus 10 is equal to root 3. Now we're not going to use this. We're going to use what we did in part A. Now in part A, I proved this identity. Now notice, actually let's rub that out. Notice I've got 2x here, 2x here, and then it became x on the other side. I've got something similar, but where there was a 2x, there's a 4x plus 10 instead. That means that instead of writing this long identity, I can do cot of half of this. So basically what we're doing is we're saying let 2x equal to 4 theta plus 10, which means that x is equal to 2 theta plus 5. So this cosec 4 theta plus 10 plus cot 4 theta plus 10 is actually equivalent to cot 2 theta plus 5. So this is what we're going to solve. The cot 2 theta plus 5 equal to root 3. So the first thing, since we've got cot, we're going to do the reciprocal of both sides. So tan 2 theta plus 5 is equal to 1 over root 3. We're going to do the tan inverse of both sides. So that will tell us what 2 theta plus 5 is. That's equal to the tan inverse of 1 over root 3. And in degrees, that's 30 degrees. So at this point, don't solve this yet. We're going to use our cast diagram, which I'll do at the top over here. So I'll put on 30 degrees, which is over here. It's in the A section, and we're solving for tan. So the other place is going to be over here. Remember, with tan you just draw a straight line. So that means that this is 30 degrees over here. We're going to adjust our range because this is the range for theta. So we're going to make it a range for 2 theta plus 5, which means that I times the two sides of the inequality by 2 and add 5. So it will be 5 on one end and the other end will be 365. So I'm only interested in this cast diagram between 5 degrees and 365 degrees. So let's try and draw what that looks like. So 5 degrees maybe starting here all the way around to 365 degrees here. So we're only looking for solutions in that range, and those solutions, there's one here and there's one here. So that gives the other solution as 180 plus 30, so that's 150. So I've got my two values for 2 theta plus 5. Actually, did I say that was 150? No, it's actually 180 plus 30. Need to learn my maths. 180 plus 30 is 210. Right, so now we can work out what theta is. So we're going to take both of these numbers here. We'll subtract 5 and then divide by 2. So 30 minus 5, divide by 2. That's 25 over 2, that's 12.5. So that gives me one solution, 12.5 degrees. Then the other solution, I'll do 210 minus 5. That's 205, divide by 2, 105 over 2. And so that's going to be 102.5 degrees. So there are our two solutions, which we'll highlight. Question 14, part 1. Caden claims that 3 to the power x is greater than or equal to 2 to the power x. Determine whether Caden's claim is always true, sometimes true, or never true. Okay, now we're talking about powers. Powers can be positive, 0, or negative. So let's see what happens when the powers are positive. Let's give an example. So let's say I choose a power of 3. I will get 3 cubed and 2 cubed. Now I know that 3 cubed is greater than 2 cubed because I have 27, which is greater than 8. And actually for any positive power, it's going to be true, isn't it? Any positive power put in there, it's going to be greater than. So true for x greater than 0 for any positive power. Okay, how about when we have x equal to 0? So we'll have 3 to the power 0 and 2 to the power 0. Those are equal because we have 1 is equal to 1. So actually that statement is true for x equals 0. So that gives us like this part, the equal to part. So far so good. For 0 or positive powers, it's equal. Okay, let's now look at negative powers. So let's choose a negative power of x equals -2 and see what happens. So I'll have 3 to the -2 and 2 to the -2. And actually 3 to the -2 is less than 2 to -2 because you're going to get 1/9 and we're going to get a quarter, and a ninth is less than a quarter. So this is not true for x less than 0. So our conclusion is that this statement is sometimes true, because it's true when x is positive or 0, but it's not true when x is negative. Part 2. Prove that square root of 3 is an irrational number. Now this is a proof by contradiction, so we start by assuming that root 3 is rational. Now if root 3 is rational, that means that root 3 can be written as a fraction, and we'll call that fraction a over b, where a and b are integers. a over b is in its simplest form, so it's been simplified. Another way of saying that is that a and b don't have a common factor, or their highest common factor is 1. It all means the same thing. So next step is we're going to take what we've written down and we'll multiply both sides by b. So I'll have root 3 times by b is equal to a. We'll then square both sides, so we'll get 3b squared is equal to a squared. Now you've got 3 times something gives you a squared. That basically means that a squared can be divided by 3. So a squared, and the way we'll write it is divisible by 3. Now if a squared is divisible by 3, that means that a is also divisible by 3. A is divisible, or can be divided by 3. Now if a can be divided by 3, you can write it as 3 times something. So we'll say that a, or let a, equal 3n. So that means that a squared is equal to 3n all squared. Right, so now if we go back to this statement here, okay, I'll just highlight that. We can now substitute the a squared that we've now got written as 3n squared into this statement. So we'll have 3b squared is equal to 3n all squared. Now if we divide both sides by 3, we'll get b squared is equal to 3n squared. That's because if I'd expanded the brackets, I'd have got 9n squared. 9 squared divided by 3 would be 3n squared. Now what does this mean? This means that we have b squared, which can be divided by 3 because it's a number that's been multiplied by 3. So b squared is divisible by 3. So if b squared is divisible by 3, that means that b is divisible by 3. Now here's our contradiction, because in the original statement we said a and b are integers where a and b is in its simplest form. I've just shown that a is divisible by 3 and b is divisible by 3. So both of these numbers can be divided by 3 and simplified, but we said it's already been simplified. So there's our contradiction. So my final statement is going to be this. Since a and b have a common factor of 3, or a and b can both be divided by 3, a over b, which we have here, is not simplified where we said it's in its simplest form. Therefore, by contradiction, square root of 3 is irrational.